You ever stop to think about how the real world, all its smooth, continuous glory, gets crammed into the super rigid digital world of a computer? I mean, how does a flowing sound wave literally become a bunch of ones and zeros? Well, that's the incredible translation we're going to unpack right now.
Yeah, just think about it for a second. The sound of my voice reaching you right now. It's a physical wave moving through the air. But for it to exist as a file on your phone or computer, it has to be turned into a digital file. Kind of seems impossible, doesn't it? But don't worry, we're about to build the bridge that connects those two completely different worlds.
And this right here, this visual perfectly illustrates the heart of the problem. Over on the left, that's the world as we experience it, right? It's an analog signal, all smooth and unbroken. But on the right, that's the world a computer understands. It's all discrete, blocky bits of information. You literally can't just pour that wave into a computer. You've got to translate it piece by piece.
So, where do we even start with a translation like that? Well, the answer is this incredibly clever process. It's kind of like taking a whole series of super high-speed photographs. The official name for it? It's called sampling.
Okay, so this is our starting point. Look at this beautiful, continuous wave. This represents basically any analog signal you can think of from the real world. It could be the sound of a guitar, the temperature changing in your room, even the brightness of the light. It's just pure, raw, unfiltered information.
All right, so to turn this into digital bits, we do something called sampling. And what that really means is we're measuring the height of the wave, that's its amplitude, at very specific, perfectly regular moments in time. The best way to think about it is like a cartoonist making a flip book, right? They don't draw a million frames, they just draw the key moments, and when you flip through them fast, it looks like smooth motion. Well, sampling does the exact same thing, but for signals.
And these are basically our camera flashes. Each one of these sharp little pulses is like a command telling our system, okay, measure the wave's value right now. And the most important part here, the key to the whole thing, is that they're happening at perfectly regular intervals. That timing is crucial.
And check out what happens when we do that. This is where it gets really cool. When we apply those sampling pulses to our original wave, we end up with something totally different. It's not a continuous wave anymore. Now it's just a series of separate, distinct measurements. But look closely. See how the height of each one of those pulses perfectly matches the height of the original wave at that exact moment in time? We've captured it.
Okay, but there's a small problem. Those pulses are super brief, like lightning fast, and that makes it really hard for a converter to get an accurate reading. So engineers added another clever step. It's called a sample and hold circuit. See this staircase shape? What's happening is the circuit grabs the value of a sample, and then it just holds it steady until the next sample comes along. This creates this nice, stable, step-by-step signal that the next part of our system can measure without any trouble.
All right, so we're taking snapshots. We get it. But here's the million-dollar question. How many snapshots do we actually need to take every second? I mean, if you take too few, you're obviously going to miss a ton of detail. This leads us to the absolute #1 golden rule of all digital conversion.
And here it is, the Nyquist sampling theorem. This is the secret sauce, you guys. This is what makes high-fidelity digital audio and video even possible. And the amazing part is, it's surprisingly simple. All it says is this: to keep all the information in an original signal, you have to sample it at a rate that's at least twice its highest frequency.
And there it is, in its beautifully simple mathematical form. All this is saying is that your sampling frequency, which we call fs, has to be greater than or equal to double the maximum frequency in your signal, fm. Let me put it even more simply. To perfectly capture a wave, you just have to take snapshots at least twice as fast as its fastest wiggle. That's it. Okay, let's make this real with an actual example. Imagine a sound is made up of these 3 different frequencies all mixed together. You've got a low one at 25 Hz, a medium one at 100 Hz, and a pretty high one at 300 Hz. So think about the Nyquist rule we just learned. Which one of these 3 frequencies is the one we need to pay attention to?
Yep, you got it. We only care about the highest frequency in the mix, which in this case is 300 Hz. That's our FM. So, following the rule, our sampling frequency has to be at least twice that. That means the absolute minimum rate to capture this signal perfectly without losing a single bit of information is 600 samples per second, or 600 Hz.
So, that rule, sampling at twice the highest frequency. It's not a suggestion, it's the law. And just like any good law, there are some pretty serious consequences if you decide to break it. And this, my friends, is where we enter the danger zone. So what happens if you just ignore the Nyquist theorem? What if your sampling rate is way too slow? What kind of digital garbage do you end up creating?
This is what happens. And honestly, this is one of the coolest and most important concepts in all of digital signal processing. So that dotted line, that's the real high-frequency signal we're trying to capture. But because we're sampling way too slowly, see how far apart those black dots are? The system basically just connects the dots. And in doing so, it creates a completely different, much lower frequency wave. It's a phantom, a ghost signal that wasn't even in the original recording.
This spooky effect has a name. It's called aliasing. It's a really nasty kind of digital distortion, where sampling too slowly creates a false alias of the original signal. You've actually seen this before. It's why in old videos, a helicopter's blades sometimes look like they're spinning backwards or not moving at all. The camera's frame rate, its sampling rate, is just too slow to capture the true motion. Okay, so we have the theory, we've got the golden rule, and we know about the big danger we need to avoid. Now let's put all those pieces together and see what a complete, real-world system actually looks like in practice. This diagram basically shows the entire journey from start to finish. We start way over on the left with some physical thing, like sound. A transducer, which is just a fancy word for a device like a microphone that turns one kind of energy into another, converts that sound into an electrical signal. That signal then gets cleaned up a little, and then it's fed into the heart of the whole operation, the analog-to-digital converter, or the ADC. This is the box where all that magic of sampling we've been talking about actually goes down.
Now, it turns out that the sampling rate isn't the only thing that matters. There are two other really important factors, resolution and aperture time. So, resolution is all about precision. Think of it as how many steps are on that digital staircase we saw earlier. The more steps you have, the more accurate your conversion is. And aperture time? That's all about speed. It's the tiny, tiny fraction of a second the system takes to capture the measurement. If your signal is changing really fast, you need a super short aperture time to avoid getting a blurry, inaccurate sample.
And believe me, this isn't just textbook theory. Engineers are making these exact calculations every single day. If a project needs a system to be ridiculously precise, let's say with a resolution of 0.01%, they can use a formula to figure out exactly how beefy their converter needs to be. And in this specific case, to get that insane level of detail, they would need a 14-bit converter. It's all about matching the right hardware to the right job.
And getting this precision right really matters, because this technology is, and I mean this literally, everywhere. We're not just talking about the music on your phone. This is the tech that powers industrial automation and manufacturing. It's inside robots. It runs our traffic control systems. It's the core of digital audio recording and even medical imaging like MRIs. So here's the bottom line. Through this really elegant process of sampling, all guided by that unbreakable Nyquist theorem, we have successfully built that bridge between two worlds. We've taught our digital machines how to listen, how to watch, and how to measure our analog world with absolutely incredible accuracy.
So, we've pretty much mastered teaching machines how to see and hear our world by turning those senses into data. Which of course brings up a really fascinating final question for you to think about. What human sense will we teach machines to understand next? Are we going to teach them touch? Or maybe even smell? The possibilities are pretty mind-blowing.